As many mathematicians have come to know, LHopitals Rule is a powerful tool for helping us discover the limits of functions in calculus. Or more specifically, it helps us determine the limits of functions with indeterminate forms. Guillaume L'Hopital lived from 1661 to 1704. L'Hopital was born in France and raised in a military family. His father, Anne-Alexandre L'Hopital, was a lieutenant general for the king's army. Thus, L'Hopital was deemed a nobleman or of somebody with higher class. We'll see how this impacts his life in mathematics very soon. L'Hopital followed in his father's footsteps and would pursue a military career. However, this did not mean that L'Hopital would be giving up his passion for mathematics. L'Hopital would even go to the extent as of studying geometry in his tent. Studying in his tent wasn't just for periods of relaxation, but it was actually a way of hiding his study of mathematics or being reserved about his study for mathematics. L'Hopital would eventually leave military service, citing that his vision problems were too much for effective service. However, for L'Hopital to leave military service primarily meant that he was probably pursuing his mathematics or mathematic career. This is the interpretation that makes most sense. John Bernoulli was a 24-year-old Swiss mathematician that was giving lectures on mathematics, specifically infinitesimal calculus. On a trip to France in 1691, Bernoulli would give a lecture where L'Hopital would attend. L'Hopital had connections within the inner mathematics and science circle within France, and more specifically Paris, so this led him to getting a meeting with Bernoulli. Bernoulli would agree to give lectures in France to a group of mathematicians and scientists, the same one that L'Hopital was a part of, for roughly about half a year or 6 months. After these lectures were completed, L'Hopital moved from Paris to his estate in Ux, or the countryside of France, and requested that Bernoulli give him private lessons. After a series of private lessons that Bernoulli would give to L'Hopital, he would eventually leave Ux in 1692 and go back to Basel, where he was originally from. This led to Bernoulli and L'Hopital communicating over letters or having conversations from abroad. L'Hopital was requested to provide a solution to a specific problem relating to curvature that he had learned from Bernoulli in the private lessons and specifically the lectures that he had given in Paris. This solution was given to somebody that had directly asked for it from L'Hopital. However, he had used Bernoulli's solution, so this ended up leading to some conflict between the two of them, as Bernoulli had heard that L'Hopital provided this solution and didn't directly give Bernoulli the credit for it. Bernoulli was upset and communication ceased between the two of them. It was not until at least a year and a half later that L'Hopital sent Bernoulli a letter in 1694 that provided an offer of payment, or 300 francs per year, for the exclusive rights to Bernoulli's ideas and discoveries, a request that meant that Bernoulli could not share his ideas or new discoveries with anybody else. Bernoulli accepts this offer. However, in 1696, L'Hopital would publish the first book of calculus that included all the primary ideas that were being discussed at the time from Leibniz and the Bernoulli family, and put them all within one book. This book included many of the ideas of Leibniz and Bernoulli, which eventually would lead to even more conflict, as L'Hopital had originally provided a solution that was Bernoulli's to the mathematics community, but then on top of that, he goes on to publish a book with Bernoulli's ideas and a few more mathematicians on that. L'Hopital gave credit in the book, even saying that he was obliged to the labors of Monsieur Bernoulli and that he had made free use of his discoveries, so basically claiming that he had used fair use on Bernoulli's ideas and Leibniz's ideas. This clearly made Bernoulli upset. However, we do not hear anything about this until L'Hopital's death in 1704. After 1704, we see that Bernoulli ends up beginning to challenge these ideas. Bernoulli would go on to argue that the work within the popular release by L'Hopital was actually ideas of his own. These were things that he had taught or were discoveries of his own. These claims were refuted by the public and often denied because L'Hopital had been the first to publish these ideas, and Bernoulli hadn't challenged them in the given time period of being published. So the public went on to believe that Bernoulli was actually not the true author of these discoveries, and that L'Hopital was. However, in 1921, there was finally a manuscript that was published, and this manuscript that was published ended up proving that Bernoulli had given lectures on these specific ideas that were presented within L'Hopital's book of calculus, or this first publishing that was by L'Hopital. So in 1921, we finally get this evidence that supports Bernoulli's claims that he actually was the author of many of these ideas, or at least the forerunner of a lot of these ideas that were being published in this L'Hopital's text. Retroactively, when mathematicians, or specifically the math and science community, looks back at this, it was because L'Hopital had provided the payments for Bernoulli's work. It was almost like an NDA agreement where Bernoulli couldn't say anything about these discoveries at the time because he was being paid for his work. But then after L'Hopital had died, he felt that he could take claim to these works, which was later proved to be true, but under that contract of being paid for his work and for the exclusivity of this work, he couldn't challenge it, or else he'd be forfeiting these payments by L'Hopital. Because of the claims being proven, now Bernoulli is given credit for a lot of these ideas that were in the first book of calculus, or this first published text by L'Hopital. So what is L'Hopital's rule? Well, L'Hopital's rule says that if we take two functions f and g, and they're both differentiable, where the differentiated g does not equal 0, and we're considering an open interval I that contains some specific point a, then we can suppose that as the limit, or x, approaches that specific a value of both of these functions, we should get 0 and 0 for both the functions. Or we can say that when x approaches this specific point a, we can get plus minus infinity for both the functions. So these are our two cases. We have the first case above here, and we have a second case here where we have 0 and 0 for both the functions, or plus minus infinity for both the functions. Thus, this leads us to actually saying that we have these two indeterminate forms. This is where we revisit that idea from the beginning of the video, and we say, we're either going to get 0 over 0 as a ratio of these two functions, or we're going to get infinity over infinity. And we call them indeterminate forms because they don't really tell us anything about a specific limit. 0 over 0 is just 0, and infinity over infinity could be just deemed as 1 or infinity. But this isn't telling us enough about what's going on within the specific function, or what values this function is approaching. So this leads us to saying that if we consider the limit of x approaching that specific point a of the ratio of these functions, well, let's just say that's equal to the limit of x approaching a of the differentiated functions, and that should get us a specific limit on this side here. So if we can differentiate both functions in the numerator and denominator and then take the limit, well, that should give us some specific limit that describes the ratio of these functions, or a specific value that this function will approach but not actually reach. So let's prove this idea of these functions here. And let's see how a differentiated function can actually go backwards and give us the ratio of the regular functions. So if we start by saying that the limit of x approaching some point a of f prime of x over g prime of x, well, we said that this was equal to, originally we said it's equal to x approaching a of f of x over g of x. That's where we want to get to. However, let's just erase this step and see if we can derive this using our knowledge of differentiated functions. Well, specifically, a differentiated function, we say that if we apply this a right away, we could apply the a in from our limit because x is approaching a, so we can sub that in for both of them. So we get f prime a and g prime a. And now, what do we know about differentiated functions? Well, we could actually state this as a differentiated function in terms of its limits, which in the numerator here, a differentiated function in terms of its limit, we have lim x approaches a. So this is almost like a back step in a way. We're almost resorting back to where we were. We can say that this is f of x minus f of a over x minus a. And this is all over the limit of x approaches a. Now we're dealing with g prime x, which is g of x minus g of a over x minus a. Now we see that they actually share the same denominators. So what we can do is we can say, let's just say that these can both cancel out because we can just eliminate both of them from here. So I'm going to eliminate this one here and this one here because they have the same denominators. We can take those two out. Thus, we get this is equal to the limit of x approaches a. And I'm only going to write it one time now because we only have a single ratio because I eliminated both the x minus a's. I have f of x minus f of a over g of x minus g of a. Now we're going to focus on this part here, the f of a and the g of a, because something actually could specifically happen here, and we're going to account for this in this case. Suppose I have a basic graph below here, and let's suppose this function is my f function, and this function here, or this curve, is going to be my g function. Well, suppose that this is point A, where it crosses the x-axis here. Then what do we consider A? Well, at this point, it has a specific value, but its function output, if we're talking about a function value, that means we're talking about an output in terms of y. So at f of a, if we were to plug in that x value in the function, we would get something that gives us an output of 0 because f of x, or f of a in this case, is equal to y. And same thing for g. We see that in most function cases, we have y is equal to the f of x, or in this case f of a, or equal to the g of a. So at that a point, we should get a y value of 0 for both of these. And thus, what we're going to actually do with this half, or this right side here, is we're just going to equate this to 0 because both of those can actually be 0. And we can specifically write that as lim of x approaching a of f of x over g of x minus 0 and then minus 0. But of course, if we have minus 0 and minus 0, we can actually just take these out of here. And then finally, we're left with exactly what we had before on our previous page when we were discussing L'Hopital's rule. We have f of x over g of x, and this was all equal to our original derived function of x approaching a of f prime of x over g prime of x. Thus, we've shown that by the definition of a derivative up here, by the definition of a derivative here, we can actually just directly prove using the definition of a derivative that these should be equivalent and that the limit should actually be proved by the differentiated functions. So L'Hopital's rule has very nice applications in modern calculus, and actually when you take your calculus courses, oftentimes they're going to give you very nice functions that differentiate, even if they have a sine or a cos or very high degree x terms or some variable term, they're going to be a really nice solution. In this case, what we're going to actually do is prove the L'Hopital's rule from the example in Analyses d'infinitesimal, which was the first calculus textbook published by L'Hopital to demonstrate this rule. So this might take a little bit of work, but let's see if we can construct this here. So he gives us a function of y is equal to this numerator denominator where x is going to approach a for the limit. So what we can do is we can start by actually writing in limit of x approaches a, and then rewrite the function. So we have 2a cubed x minus x4 minus a cube root of a times a actually just means a squared. But in this textbook, or this first textbook, it was common to write things that were squared as just two variables next to each other, so AA or XX. So if you see this AA in the top here, that's what that means. It's just basically saying a squared all over a minus the fourth root of ax cubed. Now, what we could do is we could directly apply the limit and see what this gives us. So what I'm going to do is I'm just going to directly put in a for all the x's and then see what this simplifies to. So I'm going to have root of 2a cubed a minus a4, because we're putting in a for all the x's, minus a cube root of a cubed, or specifically more, a squared times a, over a minus the fourth root of a times a3. Now let's simplify this here. We get that this is equal to, the first root is going to be 2a to the 4 minus a to the 4, which means we just have square root a to the 4 minus a cube root of a cubed all over a minus the fourth root of a to the 4, because a times a3 is just going to give us a4. Now this is going to simplify to a squared. The cube of a cubed is just a, and a times a is a squared, so we get a squared over a minus the fourth root of a to the 4 is just a. Now we have a squared minus a squared is 0, and a minus a is 0. So we have this first indeterminate form of 0 over 0, meaning that we have to differentiate both the numerator and denominator in order to progress on this, because 0 over 0 is an indeterminate form and it doesn't tell us anything about the limit. All it says is that we need to differentiate using LHopitals rule. So now if we go below here, let's differentiate the numerator and denominator. So I'm going to have the limit of x approaches to a of, now I'm going to rewrite, I'm going to take this same original function, but instead rewrite it here. So we have root 2a3x minus x to the 4 minus a cube root of a squared. Remember, a times a was just a squared, and then times x, all over a minus the fourth root of a times x cubed. Okay, so we got a bit of work to do here, but let's consider the numerator to be f and the denominator here to be g. If we can do this, then finding their primes, or f prime and then g prime, this should be fairly easy knowing that we have identified both of them here. In the case of this function, what we're going to have to actually do is, L'Hopital's rule says that we differentiate each independently. So we're not going to be using quotient rule here like you would use in a traditional calculus course. What we're going to have to do here is we're going to have to say, let's differentiate these independently. So let's consider f first of all, or the numerator. If I differentiate this, I can actually rewrite this term as 2a3x minus x to the 4 to the 1/2. That's the same thing. That's saying we're square rooting this. And then similarly, what I'm going to do is I'm going to go minus a bracket a squared x to the 1/3. I'm just going to take each of the roots and then convert them into exponents. Now that I've done this, let's take the derivative of each. So to do the derivative of something with a power, we have to use the power rule in this case of, we're going to drop the power, subtract 1, and then derive the interior in terms of x. So I'm going to drop 1/2 out in front. I'm going to rewrite all my same terms. But then now I have to derive the interior and multiply it by that. And excuse me, I'm going to have to subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. And this is all multiplied by the interior derivative, which is going to be 2a cubed, because the derivative, we consider a to be a constant in this case, and the derivative of x is just going to give us 1. And then we have minus 4x cubed because we subtract 1 from the exponent, drop the exponent for derivative. Now we're going to subtract 1/3 a, and all I did was move the 1/3 down. In the brackets, I'm going to keep the exact same thing, but then I need to subtract away 1 from 1/3. That's going to give me a value of negative 2/3, and then the interior derivative is going to be, well, the derivative of x is just going to give us 1, so we get a squared. I'm going to try and combine what I can combine, and then let's see if I can move the denominator down. So in the terms of what this simplifies to, I'm going to have 1, or let's multiply this, 2a3 minus 4x to the third over, we're going to have 2 times this 2a cubed x minus x to the 4 in brackets, and then this is going to be subtracted by, the a's are going to stay in the numerator, so we get a cubed over 3 a squared x to the 2/3. And this should actually be to the 1/2 as well down here. So we have everything we need in terms of our f to simplify this. And then now let's do the derivative of g, and we'll see if we can put these together here. G from above is just a minus the 4th root of ax cubed. If we take g prime, or the derivative, then the derivative of just a constant 0, and then all we're going to be left with is the second part of the negative 4th root of a minus x cubed. So just like what we did before, I'm going to actually convert this into exponential form, which is going to give me a quarter here. Now I'm going to drop the quarter. So this is going to be, in the second line, I get negative 1/4, keep everything on the interior of the bracket, subtract 1 from the exponent here, which is going to be equal to negative 3/4. And then I have to multiply by the derivative in the interior, which is going to be 3ax squared. And that was just from dropping the 3 from the x exponent and then subtracting 1. And that's as much as we can really reduce, but what we could do is do similar to what we've done in the f prime, and we can say negative 3ax squared, because that all stays in the numerator, but everything attached to that fraction, or specifically the negative exponent, that's going to go to the denominator. So we get 4ax cubed to the 3/4, positive now. So we have our two components we need to put in our ratio here. We have our f prime described here, and then we have our g prime described here. Now, of course, they have two variables, or seemingly variables, included with them. We have a and x. However, treat a like it's just some arbitrary constant and that it's not actually another variable, or else we would have had to do a bunch of chain rule and power rule. But in this case, what we can do is we can actually just treat it as a constant, and that constant will be involved in our solution. So now let's put these two pieces together that we've solved. If we put them together to find our specific limit, we say that our specific limit is lim of x approaching the value of a, where our f prime is in the numerator and our g prime is in the denominator. So this is going to be equal to the limit of x approaches a of, well, f prime, everything f prime is this 2a cubed minus 4x cubed over 2 times 2a3 x minus x4 to the 1/2 minus a3 all over 3 a squared x to the 2/3. So that was just f. Now we have to put in g. G is equal to negative 3 ax squared over 4 ax cubed to the 3/4. Now let's actually see, before we do any combining or see if we can simplify, let's actually plug in our limit or plug in the value of a. So now we have 2a cubed minus 4a cubed, because now we're plugging in the a's, and I'll put brackets around everywhere where I plug in the a's, all over 2 times 2a cubed a minus a4 to the 1/2 minus a cubed over 3a squared a to the 2/3 all over negative 3a squared over 4a cubed to the 3/4. Very complicated stuff, as you can see, but we're making it do. So everything that I've plugged in for the a, or all the x's I've replaced, they had a's in brackets. Now let's see if we can simplify this. In the numerator of the first one, or specifically here, we see that we have 2a cubed minus 4a cubed. That's going to give us negative 2a cubed. The denominator of that, well, if we apply the square to each of these terms, we have a 2a4 here. This will simplify to 2a4. And we have a minus a4. So singularly, 2a4 is minus 1a4. That's just a single a4. And that's raised to the square. So now we get left over, because of the 2 on the outside is going to combine with that interior, we have 2a, and this is going to be squared. So that's our first fraction here. And then we have minus a cubed over the interior of the brackets is going to be a cubed. So the interior here becomes a to the third. A to the third raised to the 2/3. Well, the 3's of each of these are actually just going to cancel. We'll see that 3 here and the 3 here cancel. So now we're just left with 3a squared. And this is all over 3a cubed over, because the a squared and the a are going to combine, over 4. The interior of the brackets becomes a to the 4, and similarly what we did before, so if this becomes a to the 4, then the 4 in the numerator and denominator are going to cancel of the exponent and the one within the brackets, and we're going to be left with a to the 3. Perfect. We're almost there. We're getting close. Now, let's simplify what we can of the individual fractions here. If I want to combine these, what I can do is I can reduce them and then figure out a common denominator. So maybe that's what I'll do. I'll reduce the a's as much as possible and then see if I can create a common denominator. So in the in the first fraction here of f, I'm going to say that the 2's are going to cancel and 2 of the a's are going to cancel, meaning that we're left with 1a and a negative. So my next line would be negative a minus, well, same thing on the right hand side here. We're going to say that the 2's will leave 1a, and then the 3 technically can't cancel here, so we're going to be left with a third. So we have a over 3. And if we want, we can even say that this is over 1, but it's just 1 over 1. But let's leave it as that for now. In the denominator, we're going to see that the a3's both cancel, and we're left with 3 over 4. Now, let's deal with the numerator here. The numerator is going to be negative 1 minus a third. And this 1 minus a third, well, that's going to be equal, or negative 1 minus a third, that's going to add a third to this. So if we consider this first fraction, we can consider this one. If it's 1 over 1, we can multiply the numerator and denominator by 3, maintaining 1. So we say that negative 3 over 3 minus 1 over 3, that's going to give us negative 4 over 3. So we get negative 4a over 3 all over 3 over 4. Now let's reduce this. So if we have two fractions over each other, I'm just going to put that second fraction to the side. So I have negative 4a over 3 divided by 3 over 4. And now if I do the kiss and flip rule, I'm going to have negative 4a over 3. And this is going to be times 4 over 3. When I multiply this, I get 16a over 9. And let's just make sure that I included all the proper signs. It looks like I forgot a negative here because we should see that the negatives cancel. So there will be a negative in this denominator here, meaning there's a negative here, and those two negatives cancel. And finally, as a solution, the limit of L'Hopital's rule, according to his example from his first textbook of calculus, is this 16a over 9.